Hi everyone, this is the topic Exponentials and Logarithms. This is a topic for the International Baccalaureate course, Mathematics Standard. So we've got quite a bit to cover in this topic. We're going to start with exponents and laws of exponents. Then we're going to introduce logarithms and look at the logarithm laws. We'll look at the change of base rule and then the graphs. And then natural exponent, which is E, natural logarithms, exponential equations, and finish off with growth and decay. So let's begin. An exponent is the name for an index or power. And for example, 2 to the power of 5 is a short way of writing 2 times 2 times 2 times 2 times 2. And in this case, 2 is called the base number and 5 is the exponent. And we've got other words for this exponent. We also call it an index or a power or an order. The exponent laws, if m and n are integers, are as follows. If we multiply pronumerals or numbers that are the same, we add the exponents. If we divide numbers or pronumerals that are the same, we subtract the exponents. And if I raise a power to a power, I multiply those powers. There are a couple of identities as well. So remember that anything to the power of 0 is equal to 1. This is the reciprocal identity. So a to the negative n means the reciprocal of a to the n, or 1 over a to the n. And this one here, a to the 1 on n, that's going to be the nth root of a. Okay, let's look at some examples. So expand and simplify 3 to the x multiplied by 1 minus 3 to the y. So I'm going to go 3 to the x times 1 minus 3 to the x times 3 to the y. Let's have a look at it. This first term is easy, isn't it? It's just one lot of 3 to the x. And I've got a minus, and now I'm multiplying these two together. So when I multiply numbers that are the same, I add the indices, or add the powers. So there we are. Now in this case here, I've got 1 minus 2 to the x all squared. So that's 1 minus 2 to the x multiplied by 1 minus 2 to the x. And you could do FOIL on that, but there is a shortcut and we need to learn this. So I'm going to go 1 squared minus 2 times 1 times 2 to the x plus 2 to the x all squared. Let's have a look at it. So there's my 1 squared minus 2 times 1 times 2 to the x, and then plus this last term squared. So this is raising a power to a power. And remember, we multiply those powers. Tidying it up, a lot of people would want to write 4 to the x here, and it's not true. So this is 2 to the power of 1. So when I multiply numbers that are the same, I add the powers. So it's actually going to be 1 take away 2 to the x plus 1 plus 2 to the 2x. Okay, what about this one? So in this case, I could do FOIL on it. First, outer, inner, last. But this is a difference of 2 squares, which means that the outer term and the inner term are going to cancel. So all we have to do is the first and the last. 1 times 1 is 1 minus x to the half times x to the half. And I just need to tidy this up. When I multiply pronumerals that are the same, I add the exponents. A half plus a half is 1. So that's equal to 1 minus x. Let's look at factorizing. So in this case, I want to factorize 2 to the x minus 2 to the x plus 1. So we need to remember that this is 2 to the x multiplied by 2 to the 1, or 2. So 2 to the x is a common factor. So I'm going to bring that out the front. This first bit's easy. So 2 to the x multiplied by 1. Take away, and this is 2 to the x times 2. So you can see how I've multiplied it there by the 2. I can tidy that up, can't I? 1 take away 2 is negative 1. And so the whole answer is negative 2 to the x. Okay, here's a rather complicated one. It's a quadratic. It doesn't look like a quadratic, does it? Here I've got 3 to the 2x, and here I've got a 3 to the x. But the trick to these ones is realizing this is 3 to the x all squared. So let's rewrite that. So can you see I've got sort of like an x squared minus 8x minus 9 sort of thing? So I can just pretend this is just an x and factorize it into two brackets. So I'm going to have different signs. 9 and 1 is going to give me the 8 that I require here. So it's going to look like this. Let's just have a look at that. 3 to the x times 3 to the x is 3 to the x all squared, plus 3 to the x minus 9 lots of 3 to the x is negative 8 times 3 to the x, and then the last term is going to be minus 9. You need to practice a few of those. Also be aware that they could write this question like that. Okay, can you see the 3 squared there is 9? Okay, if they do it like this, you need to then put it in this form and then switch the powers around like that in order to be able to do this. Now a logarithm in base A of B is written like this. And some important notes about logarithms. This base A has to be greater than 0 and it can't be equal to 1. And this here, this B, is always going to be greater than 0 as well. A logarithm is the inverse operation of an exponential. So far in our mathematical journey, we've learnt that plus and minus are inverse operations, times and divide, square and square root. So here's another one, logs and exponentials. When we apply a logarithm to a number, we strip off the exponent. So that means that log base 2 of 8 means 2 to the power of what gives me 8? 2 to the power of 3 is equal to 8. Can you see how this is the power? 2 to the power of 3 is equal to 8. So it strips the exponent off the number. Now if you take nothing else from this video other than this is important. Okay, this is the key to unlocking logarithms. If you always come back to this means 2 to the power of what equals 8, then you'll be able to understand what you're doing. Let's have a look at some other examples. Log base 4 of 16. 4 to the power of what equals 16? Well, that's 2. Base 3 of 81. That's 3 to the power of what is 81? Is 4. What about this one? Log base 10 of 100,000. 10 to the power of what gives us 100,000? Well, that's 5. Now there are 2 log buttons on the calculator. So this first one here, log, is base 10. And if ever you see log just written without a base, it means base 10. This one here, ln, ln, is log base e. And we're going to talk more about what e is later on in the video. So base e and base 10. But there are other bases available on the graphics calculator. So this is what you do. You go into the run section of the calculator and there's a logarithm option under F4, which stands for math. And then you would hit F2 for log base A of B. So a little bit like this. So there it is there, you can see it. So you would then fill in these, say I wanted log base 2 of 17, and then hit enter or exe, and then it'll come up with our number. But beware, many of these questions will be in the non-calculator paper, so you won't have access to your graphics calculator. Now we can change from exponential form to logarithmic form and vice versa. This is really useful. So we might have log base 2 of 32 equals 5, and we might want to write that in exponential form. So all we do is what I taught you before. 2 to the power of what equals 32. And there's our answer. So this is index form or exponential form. This is logarithmic form. And these two are actually equivalent expressions. Let's go the other way and write in logarithmic form. Now the trick to this is to pick up which number is the base. And you know this from the previous work you've done with indices or exponents. This is the base number. So this is going to be log base 5 of 125 equals 3. How about this one? Where's the base? Here. So log base 3 of a third equals negative 1. This one, log base 15 of 1 equals 0. And finally, this one. This one's back the front. Can you see that? Here's my base number with my power and what it's equal to. So here's our base here. Log base 5 of root 5 equals a half. And that's going to lead us nicely into some basic identities. So let's have a look at these. When these two match, this is equal to 1. Let's have a look at y. M to the power of what equals m? 1. M to the 1 is equal to m. This one, log base m of 1 is equal to 0. M to the power of what equals 1? M to the naught equals 1. Here I've got the reciprocal one. So this is m to the power of what will give me 1 over m. Well, m to the negative 1 will give me 1 over m. Here's the fractional index. M to the power of a half is equal to the square root of m. And here's just a couple of ones that might help you with cancelling later on. When I've got log base m of m to the n, that's equal to n because I'm stripping off this power. This is saying m to the power of what is equal to m to the power of n. Just let's write that out, see if you can make sense of it. M to the power of what is equal to m to the power of n. Can you see that the what there is n? So effectively, this cancels out. And then finally, this last one is kind of the same thing in reverse. M to the power of log base m of n is also equal to n. Again, you've sort of got a cancelling out thing happening here. Okay, there's a change of base rule. So this is a way of taking a logarithm and changing the base of it. Really useful if you don't have a graphics calculator and you've only got a scientific calculator and all you have access to is the log base 10 and log base e buttons. So here's the rule. Log base a of b is equal to log base c of b divided by log base c of a. Let's see how we use it. Convert log base 200 to base 10 and then evaluate using a calculator. So I'm going to take this and I'm going to convert it to base 10 like this. Okay, so it's got the new base. And it's going to have 200 up here divided by, and then log base 10 of 2. And then putting it into the calculator, I get 7.64. They could ask you to do this in a non-calculator paper. Obviously in a calculator paper, you don't need to because you can get this straight away on your graphics calculator. Let's move on to the log laws. Just like the exponent laws, there are 3 log laws, and they're fairly similar. So here I've got a multiplication, here it becomes an addition. Here I've got a division, it becomes a subtraction. And here I've got a funny looking thing. We've got a subscript, a normal number and a superscript. And this index here or power comes out the front. My year 10s have nicely renamed this as the clog law, which I think is rather amusing. So when I've got log base a of a product, I can separate it into 2 logs that I add together. When I've got a quotient like this, I can separate it into 2 logs that I subtract. And this one, where I've got this ABC thing, the C comes out the front. Let's have a look at how we might use them. So here I've got log base 10 of 5 plus log base 10 of 20. So I've got an addition of 2 logs. I can multiply the 5 and the 20 like this. 520 times 20 is 100. Log base 10 of 100 is 2. How about this one? Okay, very first thing before I can do this division here, well, what will become the division is I've got to get rid of this. So this is going to come up the top here as a power. So this 3, actually I'll draw that out for you. But come up here. And 3 cubed is 27. So you can see what I've done there. Now it's a division. So it's going to be log base 2 of 27 divided by 9, which is log base 2 of 3. And that's actually as simple as it's going to get. On your formula sheet, you get this. So we've got these equivalent expressions. exponent form and log form, the 3 log laws, and the change of base rule. Let's move on to graphs. So the exponential graph y equals 2 to the x looks like this. So I've got a y-intercept always at y is equal to 1. I've got an asymptote at y equals 0. The domain is all real numbers and the range is y is greater than 0. Given logarithms and exponentials are inverse functions, the log graph will be identical in shape to the exponential graph, but reflected in the line y equals x. You can see that on this graph. So here I've got y equals 2 to the x, and here reflected over that line I've got y equals log base 2 of x. And some of the features have flipped around as well. So for this graph, y equals 2 to the x, I had a y-intercept of 1. Now I've got an x-intercept at 1. The asymptote for this exponential graph was y equals 0. The asymptote for y equals log base 2 of x is x equals 0. And the domain and range switch around as well. Let's have a look at these two. So the domain for y equals 2 to the x was all real x. That's become the range for log. And the range for y equals 2 to the x was y is greater than 0. That's become the domain for y equals log base 2 of x. Now recall that inverse functions will satisfy this rule. So basically what this means is that I take a constant, say a, substitute it into the function, take the output of that function and substitute it into the inverse, and I should end up back where I started. Find the inverse function of f of x is equal to log base 2 of x and use the above rule to prove that they are inverses. Okay, so I'm going to start with y equals log base 2 of x instead of f of x and switch the x and the y. Now I'm going to write this with y as the subject, and this is actually just about taking it from log form back to index form or exponent form. So 2 to the x equals y. And now that that is an inverse and it is a function, I can replace it with f to the negative 1 of x is equal to 2 to the x. All right, second bit, we now want to use the above rule to prove that they are inverses. So here's our two functions. F of x is equal to log base 2 of x. F to the negative 1 of x is equal to 2 to the x. All right, I'm going to take a and substitute it in here, like that. Now I'm going to take the answer and substitute it in here. So I get f to the negative 1 of log base 2 of a will equal 2 to the log base 2 of a. And that's one of those identities that I mentioned before. These two cancel each other out. So that's just equal to a. So because I have taken a, substituted it in there, then substituted it in there, and ended up with a, then they are inverses. So let's move on to the natural exponent e. The natural exponent e is an irrational number like pi. It was initially discovered by Jacob Bernoulli in 1683 when he was studying compound interest. So hopefully what you remember about compound interest is that the more often it's compounded, that means calculated and put into the account, the more interest you'll earn. And in fact, the maximum interest that's possible to be earned will occur when the interest is compounded continuously. Now here's where E comes into play. If we're given any interest rate R and a term N, then a maximum amount accrued at the end of that term can be expressed like this. So I've sort of taken the compound interest formula, P times 1 plus R to the power of N, and if we make it compound continuously, we start to get this number here. And this is E. So let's go through this. Suppose $1,000 was invested at 6% for 5 years. Calculate the amount accrued given the following compounding frequency. So here I've got in my table that it's compounded annually, quarterly, monthly, daily, hourly, and each second. So annually means 1 time a year, quarterly is 4 times a year, monthly is 12 times a year, daily is 365, and then hourly is 365 multiplied by 24 etc. Now this is a rather more extended form of the compound interest formula. So I've still got the amount accrued is equal to the principal multiplied by 1 plus r, but I'm dividing by the number of times it's compounded. So if it was quarterly, I'd divide by 4, monthly I'd divide by 12, and then I'm raising it to the power of nt, so the number of years multiplied by the number of times it's compounded. And using this, I'm going to work out what amount will accrue after the 5 years given this compounding frequency. So just using a calculator, if I do it annually, I get $1,338.23. Quarterly is a little bit more, $1,346.86. Monthly, a little bit more. Daily, $1,349.83. And then hourly and each second starts to level off. Now, if we work out, I put this formula on the previous slide, the amount accrued is equal to the principal and then e to the power of rn. Then I put the numbers in. So there's my 6% and my 5 years. Look at that. Get the same amount. So basically what this is saying is that any interest rate can be expressed with as e to the power of that interest rate times the number of years. And this will give us the maximum amount of interest. So that's where e comes into play. Which brings us to the natural logarithm. The inverse function of the natural exponent, e to the x, is the natural logarithm, which we write as log base e of x, or ln x, which we met earlier in the video. And note that x has to be greater than 0. So we might want to find x if ln x is equal to 2. And all we're going to do here is turn this from logarithmic form into exponential form. Remember, this is log base e, so it's going to be e to the 2 equals x. So I've just turned that around. Now on the calculator, what you do is just above the ln button, you'll see e, so you go shift and then hit that button and then put a 2 in and press equals. And so x is equal to 7.39. Now, not surprisingly, we can use the log laws with ln x as well. Here's an example. Show that ln of 1 divided by root 3 is equal to negative ln 3 divided by 2. When we're trying to show that two expressions are equal, we start with the left-hand side, work it through until we get the right-hand side. So let's start here. Okay, the first thing I can see is that this is 1 over. So that's going to be root 3 to the negative 1. Now this negative 1 can come out the front. The next thing I can see is that I've got the square root of 3, which is 3 to the half. And then finally this half can come out the front. I could write that as negative a half ln 3, but I want it in this form here. So I've got the negative, and I've just absorbed that 1 up the top, 1 times ln 3. And so I've shown that this is equal to this. So let's move on to exponential equations. This is one of my favorite applications of logarithms because it makes solving exponential equations so easy. Here's an example. Solve 3 to the power of x is equal to 17 and give your answer to 2 decimal places. So previously, if you didn't have logs, you'd have to use guess and check, which is tiresome to say the least. But now that we've got logarithms, we can take logs of both sides. So we start off with 3 to the power of x is equal to 17 and then take logs of both sides. It doesn't matter what base you take. So if you take log 10 or log base e, then you can do it on the calculator. If you take log base 3, this whole side will collapse to being x. It's up to you how you want to do it. But from here, I can bring the x out the front and then divide both sides by log base 10 of 3. And then on the calculator, that's going to give me 2.58. So see how easy that is? So previously, if you'd wanted to get that to 2 decimal places, you would have been starting off, okay, 3 to the power of something equals 17. Well, it's going to be somewhere between 3 squared, which is 9, and 3 cubed, which is 27. So let's guess 2.5. And then you would have been guessing, checking until you could get it accurate to 2 decimal places. So this is much simpler. So earlier on in the video we tackled a question like this where we had to factorize. Now we have to solve the equation. And it's telling us to make an appropriate substitution and solve this. So remember this was 3 squared to the power of x, and I've got another 3 to the power of x here. So that's going to be my substitution. Let m equal 3 to the power of x. Now I'm going to rewrite this, change this around. This is going to be 3 squared to the power of x, and I'm going to flip around the indices. See? Which is fine, because x times 2 is the same as 2 times x. So this is still 3 squared, which is 9 to the power of x. Now instead of that 3 to the x, I'm going to put m. Now I try and factorize that into 2 brackets, but unfortunately it doesn't factorize, so I'm going to use the quadratic formula. So it's going to give me minus 6 plus or minus the square root of 36 minus 4 times 1 times negative 4 divided by 2. Tidying that up, I get this. So m is equal to 0.606 or negative 6.606. Now we're not finished here because we want to figure out what x is equal to, not what m is. So I'm going to take each of these in turn and see whether I can get any solutions. Okay, so there's our 2 solutions. So we're going to say let 3 to the x equal to this, and also 3 to the x will equal this one here. So here's the first one. Now, how do we solve that? That's just an exponential equation. So we're going to take logs of both sides. So it's x log 3 equals log 0.606 divide by log 3, and I'll get negative 0.456. When I take the other one and I try and do logs of both sides, I get log of a negative number, and that won't work. If you try and get that on do that on a calculator, it's going to give you an error. So there's actually no solution to that one. So x is equal to negative 0.456 is actually the only solution. Now, growth and decay are applications of exponential functions, and they're typically going to be of the form y is equal to a times b to the power of t. Y and t are variables. Y is the amount of the substance or the thing, and t is time. A and b are constants. Now a is the initial value, that's when time is 0, and b is either the growth factor, in the case where b is greater than 1, or the decay factor, when b is less than 1. So if it's greater than 1, we're talking about compound interest or population growth or inflation or bacteria. If it's less than 1, typical applications are depreciation or carbon-14 dating. So let's look at an example. A plague of rabbits is increasing according to the function r is equal to 2 times 1.5 to the power of t, where r is the number of rabbits and t is the time in months. Part A, sketch a graph of the function and describe its features. So it's roughly going to look like this. It's going to start here at 2, and I can tell that because this is when t is 0. 1.5 to the 0 is 1. And so the number of rabbits that you have to begin with is 2 rabbits. And then it's going to increase rapidly from there. We don't have to be too precise with this graph. When it says sketch, you just have to put the important features in. Okay, so the y-intercept is 2, which is the number of rabbits at time 0. And the graph is increasing at an increasing rate. We're going to get more into this when we start calculus and we talk about rates of change, but let's just throw that in here at this stage. It's not a constant rate, that would be a straight line. It's an increasing rate. It's accelerating. Part B, how many rabbits will there be after 2 years? So remember t was in months, so we want to substitute in t equals 24. So we just do 2 times 1.5 to the power of 24, which equals 33,700. Part C. How many years will it take for the number of rabbits to exceed 1 million? So in this case, we're going to substitute in for R. So 1 million is equal to 2 times 1.5 to the t. This is an exponential equation. Let's take this 2 over first of all, and then take logs of both sides. And so that'll give us this. And then we're going to divide both sides by ln 1.5. I've just turned it around. Put it into the calculator. and we get 32.4 months, which is equal to 2.7 years. So one application of growth and decay is Newton's law of cooling. Newton's law states that the temperature of an object will tend towards the ambient temperature of the room. So basically, if you put a hot object into a cooler room, then it will tend towards the temperature of that room and eventually get there. And the formula can be written like this. T is for temperature is equal to A plus B e to the negative kt. T is the temperature of the object. K is a positive constant. T is the time that has elapsed. A is the ambient temperature of the room. And A plus B is the temperature of the object when it is placed in the room. Now, I wouldn't worry too much about memorizing any of these because we tend to work them out from first principles. So let's have a look at an example. So a cup of coffee has a temperature of 90 degrees when it's placed into a room of temperature 22 degrees. After 10 minutes, it has cooled to 60 degrees. All right, so we're going to write an equation for the temperature T of the coffee after T minutes. All right, so we'll start with the equation I showed you just before, and we've got three constants that we have to work out. So we're always going to start with this ambient temperature. So as time tends towards infinity, the temperature of the coffee is going to tend towards 22. So I can write that like this. As time tends towards infinity, the temperature tends towards 22 degrees. Let's substitute that in. 22 is equal to A plus B e to the negative infinity. You can see how I haven't worried about the k because anything times infinity is infinity. Now what's this mean? E to the negative infinity. That's the reciprocal of e to the infinity. And this is basically 1 divided by an extremely large number. And so that's actually equal to 0. And so that's going to wipe out this term because I'm going to be doing b times 0. So there you have it. A is equal to 22. The second piece of information we have is its initial temperature. And so this is at time 0. So we want to put 90 in where t is. We know that A is 22 plus b times e to the 0. E to the 0 is 1, isn't it? So I can cancel that out. And just by solving a very simple equation, I'm going to get b is equal to 68. So there we've put in a and b, and now all we have to find out is k. And there's one more piece of information that they've given us in the question. After 10 minutes, the temperature has cooled to 60 degrees. So I'm going to put 60 in here and 10 in where t is. Okay, we've just got to solve an exponential equation now. Let's subtract 22 from both sides and then divide by 68. Make sure you keep enough decimal places here. Take logs of both sides gives us negative 10k is equal to ln 0.5588. And then divide by negative 10 and k is equal to 0.0582. So now if we substitute that in up here, we have the full equation. Okay, let's return to our plague of rabbits. As I said, it was increasing according to the function r is equal to 2 times 1.5 to the power of t. R is the number of rabbits, t is the time in months. After 30 months, the population growth begins to slow down as food becomes scarce and land is limited, and the population approaches a limit of 1 million rabbits. Draw a sketch of this scenario. Okay, so here we've got our increasing at an increasing rate up until 30 months where this is the population. And then after that it becomes increasing at a decreasing rate until it reaches a limit of 1 million. Again, you don't have to be too accurate, and you can see that I haven't here because this is 2, this y-intercept here, and that's probably not accurate compared to the 1 million. So this scale's pretty dodgy, but we're showing the general shape. Increasing at an increasing rate, increasing at a decreasing rate, up to an asymptote. E. If there are 814,300 rabbits over 36 months, find the equation for the number of rabbits for t is greater than or equal to 30. So the previous graph we showed two different functions. So one prior to t is equal to 30, and then we've got to work out this equation after t is equal to 30. It's going to look something like this. So we've got a plus b like before, then e to the negative k, and I'm going to put t minus 30 here. Now, if you've done transformations of graphs, you should know that that's going to shift this whole graph over to start at t is equal to 30. So that's all that that's doing there. Okay, let's think about what we know. We know that as t tends to infinity, the number of rabbits is going to approach 1 million. And remember, that's that there. So when I put infinity in here, I've got 1 over e to the infinity, which is a 0. So it's going to wipe that out. So a is equal to 1 million. The second thing I know is that when t is equal to 30, which is time naught basically for this equation, the number of rabbits is 383,500. So that was the number of rabbits at 30 months from the previous equation. So let's substitute that in. And this is e to the naught. Remember, that's 1. So 383,500 is going to equal 1 million plus b. So b will equal negative 616,500. Okay, so that's it there. Now we've just got to find out what k is. Is there another piece of information? Yes, there is. If there are 814,300 rabbits after 36 months, find the equation. So substitute that in, we can find out what k is. So 814,300 goes in here for the number of rabbits. And instead of t minus 30, I'm going to have 36 minus 30, which is 6. And here's our exponential equation to solve. Subtract 1 million from both sides. Divide by this number. Take logs of both sides. Divide by negative 6. K is equal to 0.2. So when we substitute that in up here, in here, that's going to be our last piece of information. So R will equal 1 million take away 616,500 e to the negative 0.2, and then in brackets t minus 30. Okay, I'm just going to finish off with a past exam question. The mass m of a decaying substance is measured at 1 minute intervals. The points t and ln m are plotted for 0 is less than or equal to t is less than or equal to 10, where t is in minutes. The line of best fit is drawn. This is shown in the diagram. The correlation coefficient for this linear model is r is equal to negative 0.998. State two words that describe the linear correlation between ln m and t. So this doesn't look like much of a logarithmic question at all. It's just asking us about correlation, so it's a statistics question. So all we've got to do is say, how close are these dots to the line and what direction is it going in? So our answer would be that it's a strong correlation and it's negative. And part B says, the equation of the line of best fit is ln m is equal to negative 0.12t plus 4.67. Given that m is equal to a times b to the t, find the value of b. Now this is the log part. Okay, let's start off with this equation here. We want to get from ln m into just m. So what I'm going to do is raise both sides as powers of e, like this. Now we know that this is going to cancel out because this is e to the log base e, so that's just m on this side. And here I can split this up into 2, like this. So remember, when I'm multiplying pronumerals that are the same, I add the indices, so there's an addition. So when I'm going the other way, I can turn it into a multiplication. All right, we're nearly there. Have a look what we've got here. This thing here is going to be a. They haven't asked us for a, unfortunately. And then this thing here, I could rewrite it like that. And that, when I work that out on the calculator, is going to give me b. So I've just turned it around. The 107's come out the front. That's a. And this is b. So b is 0.887. And there you have it.